And this is another video on lossless data compression coding, which is basically binomial series coding. Now basically the thought of coding a large number as the sum to n terms of a series is a fairly common natural one that occurs to us almost instinctively. Now, although it sounds simplistic, it is in fact a very valid and a pertinent or an extremely powerful way of coding a number compressedly, in a compressed format. Now, in this case, as the title says, the series we are using is a very popular common series, which is the binomial series. Just to refresh the viewer's memory, the binomial series is a plus x whole power n is equal to summation 0 less than equal to I less than equal to n a power n minus I times NCI x power I. Okay, so this is the general a plus x for a plus n is an integer only here. Now we are only interested in this particular binomial series for which a is equal to 1 and 1 is less than x less than 2. In fact, the objective will be to determine a fairly optimal value for x, which is even slightly less than 2. So this is the objective. Using this, now if when a equal to 1 and x is so on, the series will become 1 plus x whole power n is equal to summation 0 less than equal to I less than or equal to n NCI x power I. Okay. Now the value of now our objective is to code a number k less than m equal to 2 power L dash. It must be mapped to a value v less than s equal to 2 power L, where L dash is again much larger than L by several orders of magnitude. Now in the binomial series that we saw, we are taking n will be the value, replacing it with the value s. Since we can take, now in the binomial series itself, I varies from 0 to n, so there are n plus 1 terms. By taking the sum, we can also take up to 0 terms. So in all, the value we should, so s values will be there, which means n plus 1 will be s. So n will be s minus 1, but we account for the possibility that no term of the series is taken. In all, we will have s minus 2 terms. So that will be what will be used for n here. So here k will be coded as the largest value v for which the sum to v terms of that binomial series adds up to a value less than or equal to v less than or equal to k. Summation of all of those terms are up to v terms of that binomial series, where v is a value which is less than s. So s cannot be, even if you take s to be a 16-bit number, 2 power 16 terms, as we shall see, that is enough to code a very, very large number fairly accurately. So the number of passes required to code what is remaining will be very, very few. In a few passes you can code a very large number. So the mapping is m equal to 2 power L dash must be mapped to s equal to 2 power L. Now we determine A such that A power s equal to 2 power L dash, which implies k equal to 2 power L dash by s. Now the question is this: how big or how small we have? How big or how small should L dash be in relation to S? Now to answer this question, we require that A equal to 2 power L dash by S, right? So to answer this question, we require 2 power L dash by S must be greater than 2. In other words, L dash by S must be greater than 1, or L dash must be greater than S. Okay. We also require 2 power L dash by S less than 3, which implies 2 power L dash by S less than 2 power log 3 to Lg of 3, which is log 3 to the base 2, or L dash by S less than log 3, or L dash less than S log 3. So which gives us a very S less than L dash less than S log 3 must be true. Now we also have the other question, which is how big or how small should X itself be? We have 1 less than X less than 2, but how big or how small should X itself be in relation to L dash? So that is the other question. So to answer that question, we proceed as follows. Now in this particular series, 1 plus x whole power n is equal to summation binomial series 0 less than equal nci x power I. The contribution of the middle term here will be the largest. Now here we are taking n is equal to s minus 2, and the value of the middle term, okay, now s itself we know 1 less than x less than 2. Suppose x is equal to 1 plus y, So the value of the middle term will be s minus 2c s minus 2 by 2 2 power s minus 2 by 2 times y power s minus 2 by 2. This will be the value of the middle term. Now s minus 2c, s minus 2 by 2, we can replace it safely with 2 power s minus 2. It will be s minus 3 or 4, something like that. That's okay. So this will be nearly equal to 2 power s minus 2 times 2 power s minus 2 by 2 y power s minus 2 by 2. Now this will be the contribution of the largest contribution to the sum. To the sum will be that of the middle term, which will be around this value. Now if we require that the value of the middle term be no large, we are deliberately stipulate or impose the condition, that restriction, that the value of the contribution of the largest term should be no larger than 2 power s by 2. This is the condition we are going to impose, so that the contribution, so x can be x or y, and in turn x can be determined that way. So we require 2 power s by 2 times 2 power s minus 2 by 2 y power s minus 2 by 2 less than 2 power s by 2. This means if the value is cut down by half each time, so the number of passes will be only log s passes. So the number of bits will be fairly small compared to the number of bits in the information. If we stipulate this, so the pass, with each pass the size of the information reduced by at least half, then we'll have the following. We can simplify this to find y, or 2 power 3s minus 4 by 2 y power s minus 2 by 2 less than 2 power s by 2. Therefore y power s minus 2 by 2 less than 2 power 2 minus x, which gives us y power s minus 2 by 2 less than 1 by 2 power s minus 2, or y less than 1 by 2 power s minus 2 times 2 by s minus 2 is equal to 1 by 4, which gives us x equal to 1 plus y less than 1 plus 1 by 4 equal to 5 by 4. So we have a more better and a stricter bound for x, which is x 1 less than x less than 5 by 4, and L dash itself will be such that s less than L dash less than s log 3. So between s and s log 3 we must take a value L dash such that the value of x turns out to be between 1 and 5 by 4 excluding the endpoints, which can always be ensured for a given value of S. So S itself can be just a 16-bit number. Even a 16-bit number is sufficient. Otherwise, if you take 20 or 24 goes out to 16 million terms, it will be too much time to compute. But it will compute it fairly exactly. Now X itself can be at least a double precision or higher precision. The value of how accurately you store and represent X may be in a coded form itself, so that when you raise it to the particular power X power I and you multiply it, the precision is maintained and the integer value that you take is fairly accurate. That's all that has to be ensured when you do this. Another point now another point we should note, and which must not neglect to mention, is that we could start the coding from the middle term itself, because that will be the largest term. So and then successively code the left and further left terms to the further left and to the right. In that fashion, for any series, the sum to n terms, it doesn't matter how you sum them up, the order in which you sum them up, you generate the series, you generate the series only, but in some permuted order you choose to generate it in, you can always generate it in that order. So here in this order would be ideal, because we could start off with the smallest term, in case largest term, contribution which is the largest term. In case the number to be coded is actually lesser than this largest term, that is the contribution of this series, it will come to 0, that is 0th term, and after that you can code successively further terms to the left and to the right of the middle term of this series. This is the ideal way to go about coding this series. We could code it the other way also, just the conventional way also is possible. We could start off with the leftmost term and go to progress towards the right also. That may not be too bad, it will come out to about the same thing only. If the contribution of the largest term is the middle term, sum to all the other terms will add up to may add up to slightly more than that only. So the difference will not be much. But ideally, we could start with the middle term and code successive terms further and further to the left and to the right. So this is the binomial series. It can be used for lossless compression, coding of information.